So my name is Noah McLean, and I just finished my PhD here at MIT in isotope geochemistry. What I work on is mostly measuring uranium-lead dates and then using those uranium-lead dates to learn new things about Earth history. Uranium-lead dating uses the very slow decay of uranium's two predominant isotopes, uranium-238 and 235, to lead-206 and lead-207 over millions to billions of years. And we can use these dates, often of geological processes, to figure out how the Earth has changed and built itself over time. I started off as a undergraduate assistant in a uranium-lead geochronology lab at the University of North Carolina. And it's there where I really learned about the power of the uranium-lead system. And one of the things that I find most appealing about it is that you can use it for a wide variety of geologic problems and, all across geologic time. And you can use it to inform yourself about problems in tectonics or problems in, say, timescale calibration or the evolution of life. There's a very broad array of possible applications. I think I was a musician more than a geologist at the University of North Carolina, but then I took a really stimulating intro to earth sciences. I really liked the combination of physics and chemistry and math and the outdoors. I found those all very appealing. And that's when I decided to do graduate study in geology. Some of what I'm interested in is using uranium-lead geochronology to constrain the timing of mountain building and metamorphism. And much of my thesis has dealt with that. Another part of my thesis has dealt with how we actually measure uranium-lead dates. So we combine lots of sources of information, and oftentimes those are isotope ratios, and we use those to calculate eventually a very accurate and hopefully very precise uranium-lead date. And so how we go from all of the measurements into an accurate, precise, and interpretable uranium-lead date is also of significant interest to me. As part of the making our dates as accurate as possible, one of the things that I try to do is trace down all of the parameters that we need to calculate a uranium-lead date and to make sure that those are traceable to first principles measurements. And that's really what this study has focused on. In order to accurately measure the ratio of uranium-238 to 235, we have to use an isotopic tracer. In this case, a mixture of two synthetically produced isotopes of uranium, uranium-233 and uranium-236. So we mix the naturally occurring 238 and 235 with 233 and 236, and then measure them all together. Since we know the ratio of 233 to 236 that we put into the natural sample, we can use that known ratio to correct for the unknown natural ratio. And that's how we make a very precise and accurate measurement. So in the course of our studies, we found that the parameter that we've been using for the last, say, 30 years in the uranium-lead geochronology community, that ratio of 238 to 235, was actually too high. And there are very few, if any, natural samples that have a 238-235 ratio that is as high as that. In general, our very precise and accurate measurements show that the uranium-lead systems that we study tend to have a much lower 238-235 system, 238-235 ratio. And this is important because, again, we use that parameter to calculate uranium-lead dates, and we use those uranium-lead dates to, say, calibrate that geologic timescale, or even to inform our knowledge of the early solar system. Our new data should let us calculate more accurate and precise uranium-lead dates. And in addition, we found several new things. There is statistically significant variation inside of natural systems that we didn't know was there before, which means that we might be able to use this naturally occurring uranium ratio as a tracer for Earth system processes.